Thanks everyone for coming to my talk. The talk was originally titled Type Safety for Call by Reference Languages, but the talk was getting a bit too long, so I'm not going to be talking about type safety much. I'm going to be mostly talking about call by reference. So firstly, a bit about me. My name is Ifaz. I'm a PhD student at Maple, which is Kareem's group/lab. And I am interested in programming languages, so both design and implementation. I'm interested in type systems, particularly type systems that relate to object and memory safety in some way or the other. And I'm also interested in logic and lambda calculi and their connections, and the connections between them. So that's me. This is a picture of me from last November at CASCON. I was presenting a poster there about my proposed PhD project, but this talk is not going to be about that. This talk is mostly going to focus on this design project. So this talk is going to be about designing call-by-reference programming languages. It was originally supposed to be designing type-safe programming languages, but again, this talk is already very long, so I'm not going to be talking too much about type safety. So before I can go on with the rest of this talk, I want to ask you guys a question. Oh, wait, yeah. I'm really going to be focusing on design here in this talk. So before I go on, I'm going to ask you guys a question. What is language design? You don't have to raise your hand, just shout things at me. Any takers?
Syntax.
Syntax, coming up with syntax for a language. Okay, that's one idea.
Usable syntax.
Usable syntax. Okay, that's one idea. Any semantics of the language. What does that mean?
When I type X, what is that supposed to do?
What's that supposed to do? Yeah, some sort of thing should happen somewhere when the program is running. Okay, that's another idea. Any other ideas?
Grammar.
Grammar. Yeah, that's kind of syntax again.
Tools.
Tools. Okay. That's more on the implementation side, I would say. Like actually running programs. We're mostly going to be thinking about designing languages and what they're supposed to represent in some way. So I think that's a fair bit of like early thoughts to get out of the way. So language design, I'm gonna kind of start off with thinking about design and kind of contrasting it with implementation, because a lot of people think of it being one thing, but you really can if you want to separate the two and think of designing a language first and then implementing it later. So design versus implementation. Let's start off with design. Language design is, or at least what I'm going to think of as language design, is going to be about coming up with a non-ambiguous specification of program behavior. Okay? Kind of going back to the idea of like semantics for a language. What is supposed to happen. And by program behavior, I'm mostly going to be thinking of machine behavior, but I'm going to kind of describe what machine behavior is in a little bit. And again, I want to kind of stress this non-ambiguous part, because a lot of people get this part wrong, where they say, oh, over here this can happen, or this other thing can happen, you never know which one it is, and like we often get this part wrong, so we have to be very careful when we're designing languages that, hey, the specification should be non-ambiguous. And contrasting that with implementation usually involves coming up with a compiler or interpreter, and I guess related tooling, and this compiler or interpreter will emulate the behavior that was previously specified in the design phase. And what compilers or interpreters usually do is they implement a superset of the behavior of the specification. So sometimes the spec will leave certain things undefined, and the compiler, if it wants to, can define those behaviors, define certain behaviors for those. And we have to run these things on real computers. So we have to emulate this behavior within resource constraints. So if the spec says you should have infinite access to memory, maybe the implementation can like fudge that a little bit and say, hey, I'm going to implement this behavior, but if you're using too much memory, I'm going to throw an error. So that's implementation. But as I said, non-ambiguous and to specification, there are always asterisks around these things. We have to fudge things just a little bit, but usually in a disciplined way. So I'm going to talk about non-ambiguous a little bit more. What do we mean by that? So by non-ambiguous specification, you want your specification to have enough details so that programmers can write their programs and understand what's supposed to happen. So they should know what should be returned and what can happen at the machine level. Okay? But again, as I said, there are asterisks. We may allow some non-determinism. So oftentimes languages will say, oh, if you call a function with expressions A, B, and C, then what order they get executed is left kind of undetermined. So that kind of non-determinism is usually used. Any questions so far? No? Okay. So now that we know we have to specify program behavior, so on and so forth, what does that entail? So let's go on and think about what we must do to specify a language. To specify a language, we must specify the basic constructs of that language. So does that language have functions? Does that language have objects? So on and so forth. So basic constructs of the language. We're going to also have to specify the basic operations of that language. So what kind of things are we allowed to do? And then we have to have some way of composing these basic operations to do useful things kind of as a whole. So some sort of like sequencing or composition. And last but not least, we need some notion of an answer. This computer is going to run. At some point, it has to stop and tell you something about what it did. So it has to have some notion of an answer. Right? Like some sort of notion of, hey, I'm done computing, and here's the result. Okay. But I said we need to do all of these things. But like kind of where do basic constructs kind of live, or where do basic operations happen, right? So like already we kind of run into this problem that constructs need to be created somewhere and operations need to happen somewhere, and that somewhere is going to be an abstract machine. And I've already used this term without explaining it, so right in the next slide I'm going to explain what an abstract machine is. An abstract machine is a theoretical machine. Think automata. So it's some sort of a transition system, and it allows step-by-step execution of programs. And it's abstract in the sense that it omits many details of real hardware. It's going to only keep the details necessary for the language. And I also like to think of abstract machines as machines that run programs directly rather than at some sort of machine level. Like, we're not executing instructions in some x86 machine. We're running this program directly. And we're going to see examples of abstract machines in a bit, but for now, kind of think automata. That's where like basic operations are going to happen and basic constructs. So let's go on and design a language. So some preliminaries. In the language we're about to design, computation will be the evaluation of expressions. So this is not going to be a statement-based language like C, where you execute statements one at a time. We're going to evaluate an expression all at once. And the result of this evaluation would be computation itself. So another thing is we're going to denote expressions with E, binding variables with Y, pointers with P, and kind of an abstraction layer on top of variables and pointers. We're going to have X or F. So just kind of getting some notation out of the way. Expression Z, variables, Y, X, or F, and pointer speed. Okay? So the abstract machine we're going to use for our language is going to have 3 components. They are usually specified in a weird order. I'm going to skip the first 2 for now, but come back to them later. But we're going to be designing call by reference language, and so we're going to need a heap in our machine. And a heap we're going to think of as something that maps pointers to basic constructs of the language. And we're going to denote the whole machine in this notation. So you'll have 3 components separated by semicolons, and the heap we're going to denote by sigma. It's just kind of notation for now. But this will be a state of our machine, and it's going to change as computation.
Are 5 question marks equivalent to 3?
I was going to ask
Yes.
this question.
Yeah, well, in some sense they are and not, because this is notation, this is supposed to be words. But this component is supposed to be here, and this component is supposed to be here. But we're going to look at those in future slides. For now, we need to talk about the basic constructs, and the basic constructs need to live somewhere. That's going to be our. Any other questions? Yeah. So let's look at our basic constructs. In our language, we're going to have objects and functions as our basic construct. And we're going to denote objects with this notation. So objects are going to be name and variable or pointer pairs. So it's going to have field names, A1 to AN, and it's going to have variables X1 to XN in its definition. When they live in the heap, we're going to use pointers here. So A1 will map to some pointer, and when we're using just basic syntax or writing our programs, these are going to be just variables in our language. And then we're going to have functions. Functions, we're going to use this notation, so fun, and then some arguments, and the body of this function, which is again going to be some expression. So far, so good. So basic construct, and going back to our specifying a language slide, we have defined our basic constructs of the language. So we must move on to the next step and define basic operations. In some sense, basic operations using our basic constructs. And for that, I need to define the next component in our abstract machine, which is going to be our control term. So our abstract machine is going to have a control term here, which is going to be an expression, some other thing, and a heap. And the control term will represent what we're currently executing. Okay? That's our focus of execution right now. So now that we know where our basic operations are kind of, now we have a place for our basic operations to go in some sense. So that's going to be our control term. And our basic operations are going to be field selection and function call. So field selection, we're going to have this notation, so x.a, selecting the field A from X. And function call, we're going to call F with some arguments X1 to X. This is kind of syntax, and now we can define what actually happens at the machine level. So if our heap binds the pointer P1 to some object with the field A, which points, and since the field contains P2, we will return P2. So our machine will move from this state to this other state. So far, so good. So that's field selection, and let's move on to function calls next. So if we bind the pointer P to some function, which takes arguments y1 to yn and has the body e, then if we're calling P with arguments P1 to Pn, then what will happen in our machine is we'll take E, substitute y1 to yn with p1 to pn, so that's this notation here, and then continue evaluation. That's our basic operations, so function, field selection and function calls. So I'm going back to this slide. We're done with this second step. Any questions so far? It's just going through the process. I'm just trying to explain the process you must go through to design functions. Next, we're going to define some more complicated operations. So, some way of composing basic operations together, and a slightly more complicated operation. So, our complex operations are going to be value bindings and let bindings. So, for value bindings, we're going to have let y equals a function or object that was h in E. We're using h because these things go on the heap. And for kind of arbitrary let bindings, we're going to have let y equals t in E. So this t, this was supposed to be E, I changed it at the very last moment. So let y equals E in E, so evaluate this expression, bind it to y, and then evaluate E with whatever this kind of y evaluated to. So we'll see that in a bit. But, so value bindings are somewhat easy. So let y equals h in E. We just take E. We allocate h in our heap with a new pointer p, and then substitute y with p in the body of p. It's just allocating a function or object on our heap. Questions so far? For let bindings, we're going to need the third component of our machine. So that's going to be the evaluation context, which will be represented by E, and I'll represent the rest of the computation. And when we're evaluating let bindings, our focus of execution will change, and that's what we're going to use to change our focus of execution. So evaluation context, as I said, is going to be going to represent the rest of the computation, and it's going to be a list of let bindings. So it'll be things of the form let y equals some hole in E, and you can have more E's here, so you can have let y equals hole in E, let y equals hole in some other E, and so on and so forth until you hit an empty list. So it's going to be a list of these let frames, so-called let frames, because they have a hole in them. And it's like the evaluation context is going to, in some sense, represent what to do after we're done executing our focus of execution. So let's look at how that works. So if we have this let binding, let y equals E1 and E2, we're going to change our focus of execution to just E1 and put this let frame on our evaluation context. And then once we're done evaluating E1 into some pointer P, we're going to use this pointer P back in this E we have. So we're going to take this pointer, we're going to take E from here and replace all occurrences of Y with P in this thing. And that's how we're composing our basic operations into more complicated computation. Questions so far? Right. We have step 3 done out of 4. Now we can finally talk about, the notion of an answer, result of computation, and I'm going to talk about programs as a whole. So programs for our language are going to be just expressions, and an answer is going to be some machine state, and the answer is going to be some pointers to some heap item. That's going to be the result of computation. And we will know that we're done computing things when the evaluation stack is empty, so we have nothing else to compute further. So to run our program E, we're going to start the machine with the empty heap and the empty evaluation context. So E with empty stack or evaluation context and empty heap. And we're going to run this program until we get an answer. And that's going to be our notion of computation, notion of answering. And that's it. We've specified a language. That didn't take much, did it? So, kind of putting it all together, we had expressions, we had heap items, and we had evaluation context. So these are all the operations in our language. And all of these things kind of form what programs we have in our language. And we have some sort of specification of what happens at the machine level. So we have the 5 rules for evaluating programs. So field selections, function calls, and value bindings, lead bindings, and kind of moving from changing focuses of execution. And that's an entire language in 2 slides. Cool. I don't know. So let's look at an example program running on this kind of environment/setting. So you had a question?
No, I was reaching for a check.
Okay. So let's look at this program. So let f equals some function that takes 2 arguments and does something with the arguments. And then let y equals some object, let y4 equals some other object, and then compute this function on y3 and y4. So that's our program, and we're going to start it with empty evaluation context and heap. And the first thing is, if we're going back to our rules, we have our program in this state. So our program looks like let y equals some heap item in E. So that this is the y, and this is the heap item, and this whole thing is the E. So we take that step, we allocate f onto our heap, and substitute, now the function has a pointer, and we substitute the pointer for f in this body of the let binding. So that y equals y3 in p instead of f here, and p is called at the end instead of f. So far so good. The next 2 steps are very similar. Again, our focus of execution looks like some value binding in some expression. So we go through this step again. We allocate this p3 pointer and substitute p3 y3 with p3 everywhere. Similarly with y4, again, y4 changes to p4 and p4 is allocated. And now we can evaluate a function call. So for function calls, we must take the body of this function and replace all the arguments with, all the parameters with arguments. So that's what happens here. So we take y2.a and replace p3, p4 with, y1, y2 with p3, p4. And it goes to p4.a. And p4.a is a field selection. And so the A field of P4 contains P3, that's what's evaluated. And that ends our execution because we have nothing else to execute in our stack, in our evaluation context. So that's a program running, in some sense, at a very theoretical level. Like, we didn't think about like compiling it first and then executing it there. We just directly evaluated this function in the abstract machine. So, kind of putting it all together, this whole program completed down to this stage of the abstract. So now we had a language, and we had programs in this language, and we know how to run programs in this language. how about extending the language? What are ways we can extend the language? So the ways we can extend this language are we can add more operations to this language, we can add more constructs to this language, we can also fiddle around with the abstract machine itself. So things we can do are, for example, operations. We can add mutation, field mutation as operation in this language. We can also add funkier function calls. So we had, in our original language, we only allowed you to call functions with variables. But we can also allow you to call functions with arbitrary expressions. We can add constructs to this language, so we can add ints and floats to this language. That's not a problem. And if we're allowed to fiddle around with the abstract machine, we can also do things like local variables and environments to this language, local variables that you can mutate, and so on and so forth. So we can do a lot, like starting from this base system and extending it. So let's look at least these first few things. Let's look at adding mutation to our language. So we add a field mutation operation to this language and define, again, a step for evaluating those kind of expressions. So if we had p1.a must now be p2, then that mutation happens in our heap. So P1 originally had a field A with P3, and now it changes to P2 because we execute this. We can also add, funkier function calls. So F called with expressions rather than just variables. So how this is evaluated is if E is not a variable, then we add a left frame, change the focus of execution to E, and kind of add the frame where, after we're done executing this E to a pointer, we will go back and call the function with a pointer C instead. And over here, I didn't specify if there are more E's in here or not. So you can have more E's in here, and I didn't specify the order in which the arguments must be evaluated. That's a very standard practice, because if you do specify the order, your compiler writer will get mad at you, so you usually don't. Like a lot of very nice optimizations can happen because this order is unspecified, and if you do specify the order, your compiler writer will get mad at you. So that's kind of a very standard practice. As I said, you can also add newer constructs to your language. So you can add integers to your language. So you can extend your expression language with 1, 2, so on and so forth, and the addition operator. But you have to do a lot of other changes to make things work. So you have to change your notion of answers to answers can now be pointers or numbers. Your objects can now contain pointers or numbers. Your functions can be called with pointers or integers. And you have to also specify, earlier we only had substitution for substituting variables with pointers, and we also need to add substituting variables with integers. So it's a bit more invasive of a change. But yeah, that's the end of my talk. I hope you guys liked it. We learned how to specify languages using abstract machines. Abstract machines are automata that take steps, and the kind of abstract machines we used had heaps, and we also talked about extending. Okay, thank you.